Well, on the previous lecture I have defined what is chain complex, and I will call it simply complex. What is chain map, or I will call it simply morphism of complex. What is homology of complex? What is quasi-isomorphism? What is homotopy between two morphisms of complex? So if there is homotopy between two morphisms, these morphisms are called homotopic. And what is homotopy equivalence between two complexes? So we have proved that homotopy equivalence is in fact quasi-isomorphism, so it induces an isomorphism between homology. Then we have defined what is projective module. And what is projective resolution? We understood why any module has projective resolution and why this resolution is unique up to homotopy equivalence. So I have repeated this to say everything in English because it was in Russian and maybe somebody don't know how to translate it. I think that these are all notions introduced. So now we'll talk about derived left and right derived functors, and in fact we have defined them at the seminar, but as we need to define them at lectures too. So I recall that let f be an additive functor. Well, it can be a functor between any two like abelian categories, so probably maybe even additive categories, but in our situation it always will be a functor from one category of modules to another category of modules. Then f is called right exact. I will write simultaneously the definition left exact or exact if for any short exact sequence x, y, z. Short exact means that here we have monomorphism, here epimorphism, and the kernel of this epimorphism is exactly x, and the co-kernel of this monomorphism is exactly z. Maybe I have said too much, but so one has the sequence f of x, f of y, f of z. Here we write exact is exact in f of y and f of z. It is called right exact. Left exact is when y, and exact when this sequence is a short exact sequence too. So exact is equivalent to be left and right exact. Thus, right exact means that it preserves co-kernels of morphisms, and left exact means that it preserves kernels of morphisms. So if f is contravariant, then of course left and right exact exact is the same thing. Like if you have short exact sequence, you obtain short exact sequence when you apply the functor. Mod S is contravariant. Functor. And it is called right or left exact or simply exact if the corresponding functor from mod R up to mod S is right left exact. So in particular it is for example left exact if it sends co-kernels to kernels. In right executive, it sends kernels to co-kernels. So now we will define left-derived functors of right-exact functors, and we will define right-derived functors of contravariant left-exact functors using projective resolutions. To define other derived functors, we need injective resolutions. So, for example, to define right-derived functors of left-exact functors, we need injective resolution. It will be later. So, let f be right-exact functor. Then the derived nth derived functor, nth left derived functor L and f is defined in the following way. Left-derived functor is still a functor from mod A to mod S. If M is a R module, then and P is a projective resolution of M. Then we define L M F of M as nth homology of the complex P. In particular, the zero derived functor of f is f. Well, we haven't defined the functor on morphisms, but on objects minimum it's clear that it's f, because if you have M, you have projective resolution, yes, and here M is the co-kernel of this map. So if you define f and f is right exact, then here f of M is still the co-kernel of this map, because right exact functor pursues co-kernels. So since Fp is this complex without Fm, the homology here is exactly Fm, because it is kernel of this map, which is Fp0 factor the image of this. That is exactly co-kernel of this map. Yes. The kernel is Fp0 because here you have 0. So at the first view, the definition depends on the choice of projective resolution, but as we know, two projective resolutions are homotopy equivalent, and homotopy equivalence is still homotopy equivalence after applying f. So the homology of two projective resolutions after application of some additive functor are the same. So now we have to define this functor on morphisms, and it is not very difficult. If you have two modules, m and n, and a morphism between them, here you have two projective resolutions. Then there exist F0 and so on. Fi is from Pi to Qi such that everything is commutative. So such that F0 and so on is a morphism of complex. From P dot to Q dot, and like if you denote here, for example, pi and pi m and pi n, then f pi m equals to pi n f0. And we simply define, since it's a morphism of complexes, after applying f, it is still a morphism of complexes. So f of 0, f, and so on, from f dot to q dot is still a morphism of complexes. And so it induces a map between homology. Hn so we need to denote this map. So let us denote f dot hm f dot from hm f dot to hm f q dot, and since this is by definition one f of m, this f ln f n, so we define ln f of f in this way, and one can show it is the same proof as the proof of of the fact that two projective resolutions are homotopy equivalent, one can show that two such maps, like F0, F1, and so on, or F0 prime, F1 prime, and so on, are homotopic, and this relation is preserved after the application of the functor, and so this map doesn't depend on the choice of this lift of F to resolution.
So why is the application of the functor
Homotopy?
Yes.
Because homotopy is something like this fi minus fi prime equals to here we need d0p q, yes, q 1p. Like this difference is what is si d I minus 1p plus d iq s I plus 1. Yes. But if we apply f, this equality will become this one. And so f of s is a homotopy between fi and fi prime. So we have obtained some well-defined functor from mod R to mod S. Our next objective is to prove that if you have if you have theorem which is like one sequence for left functor. Our next objective is to prove the following thing. If you have short exact sequence of R modules, then there exists long exact sequence of S modules. Where still f is a right exact functor from mod A to mod S. What sequence like f z y f x, which is in fact the same thing as h0 f z h0 fy h0 fx. And here simply the images of these maps under F, then some connecting homomorphism, and so on. Like in these places, you simply have the images of these two maps under sorry, not here, under LIF, so it is simply L2F of x, y, z. And here some homomorphisms which appear from Lemma that we will prove a little later. Moreover, if x prime, y prime, z prime is another short exact sequence, and like here F, G, H is a morphism of short exact sequences. Morphism of short exact sequences means simply that these squares are commutative. Then all squares here I will draw are commutative. Here we simply write fz prime, fy prime, fx prime, here L1 fz prime, L1 f y prime, L1 f x prime, and so on. And here simply fh, fg, ff, L1 fh, L1 fg, L1 like it's clear that these squares are commutative because it is simply application of some functor to commutative square. But the assertion is that the squares will be commutative too. To prove this theorem, we will need two well-known lemmas. One of them is called snake lemma, another one is horseshoe lemma. So, as minimum, I will formulate them. Snake lemma is the following thing. Snake lemma is a little more general, but I will formulate it in the form I remember. Let we have such picture. Prime A, B, C. Here D, E, X, Y, Z. Where here we have short exact sequence, here short exact sequence, and here we have commutative squares. So you can take kernels and co-kernels of these maps. Let us write them. Let it be again f, g, h. Here we have kernel of f, kernel of g, kernel of h. Here we have maps on kernels. Here we have co-kernel of h, co-kernel of g, co-kernel of f, and the maps reduced on co-kernels. Then there exists such map, delta. Such that H, kernel G, kernel F, kernel H, kernel G, kernel F is exact here. In 5 rightmost No, I can't. Well, I can't formulate this lemma in this way. I think. Not right exactly. Well, we have what we have. Such thickens, I think. Well, such thickens and such thickens. So here, the above sequence is exact in B and C, and the down sequence is exact in Y and X. In X and Y. Then this sequence is exact here. Here we have exactness if yz is epi. And here we have exactness if A, B is mono. Like exactness here means again epi, and here mono, and it is more or less clear, yes, because if here you have epi, then this composition is epi, yes, and this has to be epi, because when you have a composition of two arrows and the last one is and this composition is epi, then the last one has to be epi. And here the same thing. If this one is mono, then this composition is mono, and this arrow has to be mono. This part is clear. But we will need a situation where one of these maps is not mono or epi. So now we want to prove it, yes. Like, I think that I will not check all details, so it will be such sketch of proof. how one can construct this map delta. Delta from the kernel of H to the co-kernel of F. Well, it can be constructed by so-called diagram choice. What does this mean? This means that we will take some element from the kernel of H and going through this diagram, we'll obtain an element in the co-kernel of F. So let us take some x from the kernel of H. Yes, we can apply this map from the kernel of H to C and obtain some x prime, yes. H to C. Then, since this map is epi, we can take some x prime, which is a preimage of x prime. Then we can apply the map G and obtain x3 prime. So now what? Now we can apply this map to x3 prime, yes? What is it? It is the same thing as we apply y to z to g of x2 prime, yes. But the square is commutative, so it is the same thing as apply h and this map to x2 prime. And b to c of x2 prime is x prime. It is h of x prime. It is h c of x, and it is 0 because we apply h to some element of the kernel of h. And so there exists x4 such that what?
Can you repeat why it's equal to 0?
Because we apply h to some element of the kernel of h. Kernel of h is exactly what goes to h, to 0 when we apply h.
Why is it in kernel?
Because this map is the inclusion of kernel to C. Like I haven't denoted all maps here by some letters, so when I write like B to C, it means this map from the diagram, yes? So here is the map from the kernel of H to C, which is simply inclusion of kernel to C. Okay. And we apply to it H. So there exists x4 here 2 such that x to y, it is from x of x4 equals x 3 times prime, yes. And we simply define delta of x as this map applied to x4. So more or less, this is the diagram choice. When you take some element and go where you can go and come to some point where you want to come. So we have constructed the required map delta. Now we want to prove that delta doesn't depend on the choice of anything. Like here we made two choices. We have chosen x4 and we have chosen x2 primes. And so theoretically like delta of x can depend on them, but it doesn't depend. And when we will prove that it doesn't depend, it's clear that it will become clear that delta is a homomorphism of modules, because if we have two elements and have made choices for them, they can like make corresponding choices for some and obtain the sum of elements and so on. And if you have an element and multiply by some element from the ring, the same thing. So, so in fact we need to prove many things. We have to prove that delta doesn't depend on the choice of x2 prime and x4. Then we have to prove that the image of this arrow is exactly the kernel of delta. Well, in fact, we need to prove on one side, because on another side it is the same thing. It is by duality, but still here we have to prove that here it is exact in this member and in this member, yes, and in this by duality. I think that it will be an exercise for home exercise. Like any of these assertions is easy to prove, but it will take time and there are too much of them. The idea is the same. You take an element and go through a diagram and obtain what you want. And another thing that we need about snake lemma is that this map delta is functorial. Like if you have two diagrams, I will delete this, okay? If you have two diagrams, so you have A, B, C, X, Y, Z, and you have A prime, B prime, C prime. Here X prime, Y prime, Z prime. Here F prime, G prime, H prime. So here we have kernel of F prime, kernel of G prime, kernel of H prime, kernels here I have another delta that I called delta prime. And if you have maps from C to C prime, from B to B prime, from A to A prime, from X to X prime, from Y to Y prime, and from Z to Z prime, such that everything commutes, everything is clear. What's this like? If you take any of this 1, 2, 3, 4, 7 maps and get a corresponding square, it commutes. Then these maps, of course, induce maps on co-kernels, induce maps on kernels, and so these induced maps give a morphism of exact not exact sequence between the corresponding sequences, like everything commutes. The fact that, for example, the square corresponding the map between two kernels commutes is clear because it is from construction. The assertion is that this map commutes, like you have kernel of H, delta co-kernel of F, and you have kernel of H prime, delta prime co-kernel of F prime. You have two maps here that were induced by these 6 maps. Then this square commutes. It's not very difficult to prove when you have proven snake lemma. Like one way to do this is to follow the construction of delta and understand that it gives the same thing there and there. So, if you remember the theorem that we want to prove, it's clear that this delta will become the delta from long exact sequence for right-derived functors, of course. And so this fact that this square commutes will allow us to get a commutative square there too. And another less technical lemma is the horse show lemma. That you have a short exact sequence and suppose you have here P and Q. Projective modules P and Q with epimorphism from P to X and from Q to Z. Now you write P plus Q. Here the standard inclusions, here the transact projection. Then there exists a map from P plus Q to Y that makes this diagram commute. Such that this map, of course, is epi, such that two squares commute. Well, the proof is quite easy. Well, to define a map from P plus Q to Y, we have to define two maps, one map from P to Y and another map from Q to Y. And so the map from P to Y is simply the composition of these two maps. And the map from Q to Y is simply such that Q Z such that it's trial compute, and it exists because Q is projective. Well, and by construction, these two squares commute, of course, and this map is epi by different reasons. Like probably will prove 5 lemma, and it like not a part of 5 lemma, and asserts that if you have here epi, and here mono, then this one is epi. Or simply you can take an element here, it has some image here, then it has some pre-image here, you take it, and when you subtract from the initial element, you get some element in Y that goes to 0 here. And then it is it has some pre-image in X, because this sequence is short exact, and element in X has pre-image in P. Well. So if somebody doesn't understand, then it's exercise. And it's much easier than snake lemma, of course. So now we can prove the existence of non-exact sequence, let x, y, z be a short exact sequence, then we can take some projective, some epimorphism from projective module to x, some epimorphism from projective module to z, and by Horseshoe lemma we can construct here epimorphism too. And now we apply f. Yes. No, sorry. We take kernels with these maps. Yes. Note them like kx, ky, kz. Here we have again short exact sequence. For example, by snake lemma, because here cokernels are 0, and like you have long exact sequence, but since here 0, here it's exact. And now we apply f to this diagram, and what we obtain? We obtain fx. Here is not anymore monomorphism. Here is still epimorphism because f is right exact. Here you of course have mono and epi because it is split exact sequence. And here you again have epi by the right exactness of f, and here is not it is not mono, and sorry, but I write it a little downwards. And kz, and here you don't have monos anymore. F ky, f kx. But you can take the kernels. So I don't know how to denote them. Probably let us calculate these kernels. What's this? We take x, for example, yes. We take p, like, let us denote by p0, 1. Yes, so kx is the kernel of this map, and at the same time it's the image of this map. And of course we want to show that if we apply f here, then the kernel of this map, let's denote for a while by k, is exactly h1p. Yes. Right, so what is h1p? We have to take the kernel of this map and factorize by the image of this map. Yes. Let us write here kx prime. Так. Written here. I again forgot. Like, what do you have?
Вот, который целиком слева.
This one?
Yes.
Well, we first have drawn this diagram without f, and everything was exact. Then we apply f, and in some places exactness disappeared. So here and here disappears, it's okay, and here it's okay, but we want to know what is here. And we want to show that there we have exactly L1f, L1fz, L1fx, and L1fy to have the required exact sequence. Because by the snake lemma we will have such map and obtain non-exact sequence, yes. And we want to get exactly what we want to get. What is stated in the theorem. So you have to understand that, for example, here it is L1 f of x. And to understand this, we have drawn this. And we want to understand that the kernel of this map from fkx to fp0, where p0 is the same thing as p, is exactly h1p. So what do we have? We have some well, like the image of this map is the same thing as the image of this map, yes. And this sequence is exact in fp1 and fkx. So what do we have? We have okay, we have here the kernel of this map. It would be k prime, yes. Here f0. Yes, and we have a map from here to here, because this is the kernel of this map. And if you take this composition, we get 0. And this map is happy. Why? Because it's clear that it's happy or not. Like it, well, probably there is a better explanation, but if you take an element here, yes, you go here, and since here is epimorphism, you get some pre-image here. And this pre-image go to 0, because this map is simply the composition of them. since go to 0, it lies in the kernel. And so we have here a map, yes, because this composition is 0. And we need to understand that this sequence is exact. Yes. Because the image of this map is exactly the image of this map. So what we need to show? We need to show that if we have some element in the kernel of fd0 that goes to 0 here, then it lies in the image of fkx prime, yes. But if it goes to 0 here, this means that it goes to 0 here, so it is some element from here that goes to 0, but this sequence is exact, yes. Like kx prime p1 kx was a short exact sequence, so fkx fp1 fkx prime is still exact here and here. So it is what we need. That's okay. So in fact here we have one f of z, one of y, one of x. And in the same manner, we understand it here exactly. The maps that we obtain after applying L1F to the maps between x, y, and z, and we obtain the first part of our long exact sequence. Yes. And it has the required functorial property. Well, now we want to continue by induction, yes, but it's not clear how exactly. But by induction, what we can do, we can take the sequence kx, ky, kz, and apply the same procedure. Same procedure will give us the following part of long exact sequence: L1 f kz, L1 f ky, and so on. Yes, it is exactly the application of our procedure to the short exact sequence kx, ky, kz. But L1 f kz is exactly the same thing as L2 f z, because what is kz? You take z, q, projective, then you take kz, and to continue the projective resolution of z, you simply construct here q1, q2, q3, and so on. And so this part is in fact the projective resolution of kz. So starting from the first homology of kz, like Li f of kz equals to L I plus 1 f z for I more equal to 1. Because for I0 you calculate homology here, and for that you have the map from Q1 to Q, so it differs. And for kz you don't have this map. But for I starting from 1, you calculate them in the same way. So here you have what you want, and it remains to understand that like the map here can give you a map from here to here. Yes. But it's clear by some reason, yes. Sorry. You have a map from here to here, and you want to understand that the image of this map lies here. But if yes. If you you want to show that the kernel of this map lies in this submodule, yes? You take some x that goes to 0 here, then if you go in this way, you go to 0 again, yes? Because this composition is equal to this composition. But this map is monomorphism. So x lies in the kernel of this map. And then it has preimage there because it's kernel. So you construct here a map, and now one can show that you still have exactness here and here. Simply diagram choice. We have finished with long exact sequence. So in the same way, if G R not S is a contravariant left exact functor, then we can define right drive functors M as H M P GP where P is projective resolution of M. And in the same way on morphisms. In this case, for short exact sequence, X, Y, Z, one has long exact sequence. GZ, GY, GX, R1G, Z, R1G, Y, 1G, X, so on. It can be shown in the same way, of course. Well, let us now summarize some properties of derived functors that we have proved. Let f be again right exact functor. Then the left derived functors of f satisfy the following properties. Property 0 is that L0 f equals to f. Property 1. If x, y, z is a short exact sequence, then you have long exact sequence x 0 y 0 x 1 z and so on, which is functorial. What means functorial? I have already said in theory.
So did you mean L1 of Fz? You wrote G1, G0, you mean L of
It is L.
Yeah, okay, absolutely.
And another property that we can mention is that Ln f of p is 0 for n more equal than 1 and p projective. because if you have a projective P, then P is a the complex with P in 0 degree and zeros in other degrees is the projective resolution of P. And so if we will apply F and calculate homology in degrees different from 0, we of course will obtain 0. And it's interesting that these three properties, or two, I don't know, define F uniquely. Define, not F, define the functors L and F, the sequence of functors, in a unique way. I'm not sure that what I told makes some sense. I mean that if the functors, I don't know, Tn satisfy 0 equals to F, then if X, Y, Z is a short exact sequence then there is long exact sequence T0 Z T0 Y, T0 X, T1 Z, and so on, which is functorial. Not long exact sequence functorial, of course. The construction of long exact sequence from short exact sequence is functorial. And T n of P equals to 0 for projective P, and n more equal to 1, then Tn is isomorphic to Ln F. To show this, let us take some x in mod R. Then there is short exact sequence x P kx with projective P. And if we apply now our first property, we will get long exact sequence. X, like for n equals 0, it's clear because T0 is f and L0f is f. So we need to prove for n more equal to 1, of course. Fx, fp, fkx. Here L1 fx, and here we get, sorry, T1 x. Here we get 0 because T1 fp is 0. Then we get T1 kx, T2 x, 0, T3, T2 kx, T3 0, T3 x, and so on. So we see that T1 x is the kernel of this map, and since the kernel is unique, it is L1 fx, and the functoriality gives us functoriality of this construction determine the image of T1 on morphisms too, because it is kernel, and functoriality says us that if you take some x prime and here x prime you will obtain here and here some f, yes, you will obtain here T1f. Yes. Well, here you construct some lift of f, and here then upon kernels, yes. Like 0 here, f prime, something like this. And you will obtain T1f. So T1f is defined by these properties and by the functor f. And then by induction, since T1 kx is defined, and for x prime you have this, yes, square, and it commutes. Then T2 is defined, is determined, and T3 and so on, because you have these squares. So a little fast, but more or less we have proved this theorem. We have to finish.